Thank you for a nice introduction. Originally, I am a mathematician, but my research is mainly focused on the analysis of neurophysiological signals such as electroencephalogram or EEG by using mathematical methods. And my today's presentation will be focused on a specific subset of methods called tensor decomposition. And I will try to demonstrate how they can be useful when extracting specific information from electroencephalogram. So what I'm going to speak about, in the first step, I will introduce some basic principles of EEG signal and why it is useful, which information we can extract from it. Then I will give you a very brief introduction how to transform signals to three-dimensional structures called tensors, and how to extract hidden or latent components from these tensors by using tensor decomposition methods. And after this theory, we will go through 3 or 4 real data examples. The first one will be focused on detecting of narrowband EEG oscillatory rhythms in neurorehabilitation of patients after ischemic stroke. The second one is identifying mental fatigue during neurorehabilitation in virtual reality. Then it will be detecting resting state, so-called EEG microstates. And if I will have time, I will show you how to use tensor decomposition to detect and remove eye blinks from EEG signal. So, maybe many of you know what EEG signal is. It is a signal which describes electrical activity of our brain. In this figure, you can see approximately 7 seconds of EEG signal from 10 electrodes. It means in each row you have a signal from 1 electrode. When you compare these signals, there are visible differences between them. For example, the very top one and the very bottom one. You can see that there are different oscillations, differences in amplitude, and so on. So, why we need electroencephalogram? First example is, for example, a sleep EEG signal. Maybe you know that our sleep can be divided into different states. The first state is the wakefulness, when we are not sleeping at all, but we are laying in bed with closed eyes. The second state is N1 or light sleep. Then it is state N2. Then we have states N3 and N4. In some literature, they are merged together into one state, slow wave sleep. And finally, it is REM, sleep, during which we usually have dreams. You can, here on this figure, you can see example of EEG signal during each of these states. So again, there are some differences between EEG during different states. And based on these differences or some anomalies in the EEG signal, maybe the doctors or some therapists can distinguish whether this sleep pattern is typical for a healthy subject or there are some sleep problems, maybe. Other example is that, for example, epilepsy. Again, you can see a difference between normal EEG and EEG signal of a patient during epileptic seizure. And what is the most important for my research is that there is a difference in EEG signal when we are in rest and when we are performing movement. Here I would like to highlight that our brain behaves the same when we are moving, when we observe movement, and when we imagine movement. It means that when you see how I'm moving with my hands now, the same brain areas are active as you are moving with your hands, for example. So, these differences in EEG characteristics are very useful when considering so-called brain-computer interface. It means that some software, such as computer game or something other, or hardware like robotic splint, are directly controlled by our brain activity. However, if we want to properly control the software or hardware by brain activity, we have to understand the EEG signal, what properties it have, and which parts it consists of. So, from a mathematical point of view, EEG signal consists of so-called broadband brain activity. It is something which is always present in the signal because our brain is always active. When we sleep or when we are in a resting state, our brain is never turned off. It still works, we can say. But more important are so-called oscillatory rhythms. In this figure, you have examples of 4 oscillatory rhythms oscillating on 4, 8, 11, and 14 Hz. So, from a mathematical point of view, EEG signal from one electrode in time t we can express as broadband brain activity in time t, which is some time series, plus some linear combination of amplitude and phase varying sinusoids representing these oscillatory rhythms. Each oscillatory rhythm has its typical frequency, and the overall frequency range is divided into different intervals, for each of which we have a different name. For example, maybe you heard something about theta rhythms, which are between 4 and 6.5 Hz. For us, the most important is mu rhythm, which oscillates around 8 Hz, because this rhythm is directly related with direct movement or motor imagery. However, when you look at this EEG signal, it is very difficult for us and also for trained technicians to directly see over which intervals these oscillatory rhythms are active. So, in other words, these oscillatory rhythms are hidden or latent components in the signal, and we have to apply some mathematical methods to extract them. We know that each oscillatory rhythm has 3 characteristics. The first one is time scores. It means that we know over which time intervals the oscillatory rhythm was active. For example, here you can see that this oscillation was present over the first 10 seconds. Then it was suppressed, and then we have some short bursts of these oscillations. The second characteristic is spatial signature, which tells us in which part of the brain is the source of this oscillatory activity. This signature we can graphically represent by so-called spatial map. An example is here. It is like we look on our head from above. Here you can see nose, and here are ears, for example. So you can see that in this case the activity is located in the frontal region, somewhere here. And finally, the third characteristic is frequency signature, which tells us which frequency is typical for this oscillation. In this case, we look at the argument of the local maxima, which is around 5 Hz. And from the literature, we know that this oscillatory rhythm is probably a theta rhythm because of this typical 5 Hz frequency and the activity in the frontal region. So now the question is how to detect these oscillatory rhythms in the EEG signal. EEG signal can be considered as a table, or for me as a matrix, and also for other mathematicians, with T columns representing time points and J rows. Each row represents a single electrode. So, in other words, when directly working with EEG signal, we analyze it in the time-space domain. So we are able to extract only temporal or time and spatial characteristics. The frequency characteristics are not directly detectable in the EEG. We have to extract them in a separate step. So which methods we can use for this purpose? Probably all of you know principal component analysis or independent component analysis. And there are many other, but as an example, I can mention also spatial spectral decomposition. But what's the problem here? In the principal component analysis, the extracted components or their characteristics are orthogonal to each other. This is very useful in many data sets. However, in the case of EEG signal, orthogonality does not have natural interpretation, because we can have two or more oscillatory rhythms oscillating on different frequencies, but sharing the same location. So their characteristics are definitely not orthogonal. Similar problem is also in the case of independent component analysis. Here there is assumption of independence of components. Again, it does not have interpretation in the case of EEG. So we can apply these methods. However, the latent components which we obtain by PCA or ICA are very difficult to interpret, and we have to be very careful. Spatial spectral decomposition does not have any of these assumptions. It is something like generalized eigendecomposition for mathematicians. An example of this decomposition is depicted in this figure. So this method is able to extract temporal and spatial signatures, which are depicted in the first and second row. And then we can apply, for example, a Fourier transform to extract a spectrum of the time scores, and then we obtain these frequency characteristics. So this cannot be done directly by the method. We have to do this in a separate step. The first component, again, it oscillates on 5 Hz. The activity is located in the frontal region, so we can say that it is a theta rhythm. Now, that's okay. However, the problem is with the second component. First, the spatial map is very strange. It does not have meaningful neurophysiological interpretation, and when I see such a map, I will say that it is something like noise or artifact. The second problem is that in the frequency signatures, we have 4 local maxima on 5, 8, 11, and 14 Hz. So if we would like to work with this component, it does not represent a single oscillation or a single oscillatory rhythm, but a mixture of them. And this is a problem because usually in our experiments, we need each component represents only one frequency. But this is very difficult to achieve in this method. So, EEG signal analysis in the time-space domain is okay. However, for our research, it does not bring enough information. So we need to somehow add into data this frequency dimension directly. And then we need a more flexible method into which we can incorporate constraints which are meaningful in the case of EEG signal. So instead of the raw EEG, we can work with EEG spectrum. By using a fast Fourier transform or other methods like IRASA, which is irregular resampling autospectral analysis, we are able to compute EEG spectrum. 2 examples from 2 electrodes are depicted in these figures. The very nice property of EEG spectrum is that we directly see which oscillations are present in the signal. Again, looking on the local maxima. Moreover, the raw spectrum can be further decomposed into so-called fractal and oscillatory part. This fractal part is depicted by the black curve, and it represents the broadband brain activity. It has the famous 1/f trend. The oscillatory part is that part of EEG which includes only the oscillations. So when we, for example, work only with this oscillatory part, we know that there are only oscillations which are of our interest. So how to work with this spectrum? In this case, we say that we analyze the EEG signal in the time-space-frequency domain. So in the first step, the EEG signal is divided into overlapping windows. In our case, we usually use 2 seconds. Each window is of the length 2 seconds, and the overlap is 1.75 seconds. But you can change these parameters. It's up to. This is how it works for us. Then for each time window, we compute this frequency spectrum or its oscillatory part. And finally, these spectral values for each time window and each electrode are concatenated into a 3-dimensional structure, which we will call a tensor. So its dimension, it is of the size A times J times K, where A is number of time windows, J is number of electrodes, and K is number of considered frequencies. For example, we usually work with a frequency range between 4 and 25 Hz with a step size of 0.5 Hz. So usually K is equal to 43, if I'm correct, or something like that. Okay, so now the data are stored in a 3D array or a cuboid instead of a matrix. And the question is how to detect these oscillatory rhythms, because it looks like that, or maybe such data transformation is more strange or more unnatural than this standard EEG representation as a matrix. However, it will be very useful because we have a set of so-called tensor decomposition methods. First tensor decomposition methods were developed in the 1970s separately or independently by 2 groups. The first group called this method parallel factor analysis, the second one canonical decomposition, so that's why I use abbreviation CP for this method. And in this case, the tensor is decomposed into final set of so-called rank 1 tensors. In this case, I considered only 4, and each rank 1 tensor can be expressed as an outer product of the temporal, spatial, and frequency characteristics of a given oscillatory rhythm. The mathematical formulas are above. This circle represents outer product. In the case of vectors, outer product is a standard multiplication when you have a column vector times a row vector. When we have 3 vectors, this outer product leads to a cuboid, to a tensor. So very nice on this decomposition is that each rank 1 tensor or each latent component has these 3 characteristics of oscillatory rhythms. So we can directly say with which oscillation this latent component is related. For example, this second one, it oscillates around 8 Hz, and the activity is located in the sensory motor area. So this is our mu rhythm, for example. The only parameter for this CP model is number of latent components. This is in contrast to PCA, for example, because in PCA you first apply the method and then by using some elbow diagram, you decide the appropriate number of principal components. In the case of CP, this is not possible. You have to set or decide or to choose appropriate number of latent components in advance. You can use some a priori information about the data, or there are many methods in the literature. However, no one of them is something like a rule of thumb. So it is usually recommended to use several methods and to somehow, based on their results, to decide which is probably the most appropriate number of components. The second problem with CP model is that, for example, model with 4 components is not completely included in the model with 5 components, which is also in contrast to PCA, for example. So there are also some problems, but the advantages of tensor decomposition still overcame these problems. The output are 3 matrices, each of which has F columns. It means that each column represents characteristic of 1 latent component. The matrix A, in the case of EEG signal, represents temporal signatures, B, spatial signatures, and C, frequency signatures. These matrices are estimated by using so-called alternating least squares. Maybe you know standard least squares. Okay, it is in the alternating least squares, it is a standard regression model where we, for example, fix 2 matrices like A, B, and then we estimate C. In the next step, we fix, for example, A and C and estimate B, and so we repeat this procedure until convergence. Because it is a standard regression model, it is easier to incorporate constraints to the solution than in PCA or ICA. And which constraints are meaningful in the case of EEG signal? As I said, orthogonality, okay, it can numerically stabilize the solution, or it can make the algorithm faster, but for EEG signal, it does not have interpretation. For us, more meaningful is non-negativity, because if you remember, this tensor was formed from the EEG spectral values, and spectrum always includes only non-negative values. So, because the tensor is non-negative, it is quite natural to expect that also the signatures or the characteristics are also non-negative. The second very useful constraint is unimodality. You usually apply this unimodality constraint in the third mode, in the frequency mode, because we require that this frequency signature has only 1 local maximum. Because then we know that only 1 frequency is typical for our latent component. Other constraints may be, for example, bimodality. Bimodality, it means that we have 2 local maxima. Bimodality can be used in the second or the spatial mode, especially when we know that this oscillatory rhythm is a dipole. It means that, for example, it oscillates in both left and the right hemisphere, or in two separate areas of a brain. Naturally, we can consider also sparsity, smoothness, everything what is meaningful. Okay, so on these 2 figures, you can see difference in spatial signatures when I applied the CP model with only non-negativity constraints in the spatial mode and unimodality constraints in the spatial mode. So here you can see that the area or the estimated area as the source of the oscillatory activity is smaller. So for us, we directly know that this area is very specific. Second example is bimodality constraint. Here, the spatial signature was estimated only as non-negative. In this case, we considered bimodality across both hemispheres. In this case, bimodality was considered only in the left or in the right hemisphere. So again, you can see that in these three cases, the spatial maps are more specific. The areas are smaller, so we directly know the source of the oscillatory activity. Okay, and finally, some real data example. In this case, I applied the CP model on EEG signal only from 10 electrodes located over sensory motor area, so somewhere here. Because of so low number of electrodes, we are not able to extract specific areas of the oscillatory activity. We can distinguish only whether the oscillation is located in the left or right hemisphere. But as I will say, I will explain later, for our experiment it is enough. But what is important here? You can see 9 components extracted by the CP model. For example, the first one is theta rhythm, the second one is mu rhythm. But here you can see 2 rhythms oscillating on 9.5 Hz. The first one is located in the right hemisphere, the second one in the left hemisphere, and their time scores, if we plotted them above each other, they are different. We speak about phenomenon of lateralization. It means we have the same rhythm which behaves differently in different hemispheres. This is typical, for example, for patients after ischemic stroke, because they have one of their hemispheres includes damaged part. So it is quite natural that the processes in the brain are different in each hemisphere. So this is very nice to see that tensor decomposition model is able to extract also this phenomenon. This is not possible with the standard matrix methods. Okay, so enough theory, let's go to real data application. So the first topic I will focus on is neurorehabilitation of patients after ischemic stroke and detection of narrowband oscillatory rhythms. Maybe you know ischemic stroke occurs when there is a reduction of or blockage of blood supply to a part of a brain, and because of the lack of oxygen, the brain tissue dies or it is damaged. Consequences are usually paralysis of one side of the body. When you have stroke in the left hemisphere, then you have problem to control muscles on your right side and vice versa. Then this patient have serious problems with speech, walking, swallowing. They can have also emotional symptoms, pain, and so on. So it is very important that they took part in some types of rehabilitation as earlier after the stroke as possible. This rehabilitation can include physical therapy such as active or passive exercises, visual speech therapy, and other types. But in our laboratory, we are focused on neurorehabilitation based on motor imagery. This is what I said at the beginning, or the core idea of this neurorehabilitation is that when we perform movement and when we imagine movement, the same brain areas are active. The second core idea of this rehabilitation is brain plasticity. Brain plasticity is ability of our brain to change and adapt. There is a structural plasticity. It means that the brain can change its structure by some experience or learning. And the second one is functional plasticity. It means that if some part of a brain is damaged, brain, after some training, can be able to move functions from this damaged area to some other undamaged area. And this is very important for these patients after ischemic stroke. So how this neurorehabilitation is performed. So a patient comes to our laboratory. We put on him a cap with electrodes and glasses with virtual reality. Then, in some trials, the patient is instructed either by computer or by some therapist to imagine a movement in a virtual scene. This virtual scene is something like this. So the patient see some table, or on the table there is a cap and an avatar hand, which represents patient's paretic hand. Paretic hand is the one of the patient's hands with which he or she has problems. So, for example, this patient has stroke in the left hemisphere, so he was not able to control movement of his right hand. So, therefore, there is a right avatar hand. So, the patient is instructed, for example, imagine that you grasp the cap with your hand and move it to a different corner of a table. But patient should only imagine this. He is not required to perform this movement, and usually he is also not able to perform this movement. Simultaneously, we record his EEG signal, and when we find some characteristics in the EEG signal, we know that the motor imagery was successful and the patient is rewarded by the movement of the avatar hand in the virtual reality. The avatar hand moves, grasps the cup, and moves it to a different corner. And this is repeated in 10 trials during one session, I think. But the question is, how do we know that the motor imagery was successful? We do not see into patient's head. From the literature, we know that when we observe or imagine a movement, the mu rhythm around 8 Hz, its level rapidly decreases. So, therefore, in the EEG signal, we need to detect this mu rhythm and observe its level. So, how to do it? In the very first step, or on the very first session, the patient took part in so-called mirror box training. In this case, the patient's right hand is behind the mirror. It is that hand with which he has problems. And the patient observes a movement of his healthy hand in the mirror. So to him, it looks like he's moving with his not damaged, but with his paretic hand. So, because he observes the movement, the same brain areas are active as he moves, as he will move with his paretic hand. During this experiment, we record the EEG signal, and after the session or offline, we apply the CP decomposition. So we can extract subject-specific latent components from the EEG signal or oscillatory rhythms. It is very important to do this for each patient separately because these oscillatory rhythms are subject-specific. We cannot use info or characteristics from one patient for another one. From these latent components, we have to choose the mu rhythm. For example, in this case, it was the second one. And the most important are the frequency and spatial characteristics of this rhythm. Then, during the virtual reality session, we again record the EEG signal. After, we always took 1 second of the signal, online transform it into frequency spectrum, and then apply this spatial, or then we use these spatial and frequency signatures as a linear filter, so we can say, and we are able to extract new time scores of the mu rhythm. And these time scores can tell us whether the motor imagery is successful or not, because as you can see here, there are many trials averaged, but here by the dashed line, it is the time when the patient was instructed to start the motor imagery. So it is a move command. And you can see that after this point, there is a very nice decrease in the level of mu rhythm. Definitely, there is a difference between the right hemisphere information which is depicted in red, and the blue one, which is the left hemisphere, because the left hemisphere is damaged. So also this decrease is more obvious than in the healthy part. So if the decrease of the mu rhythm is under a given threshold, we know that the motor imagery was successful and the patient is rewarded by the movement of the avatar hand. And after several sessions, we observed some improvement in these patients because after some time, they perform also some tests, neurophysiological tests. And for example, one of these tests was that they were instructed to move small cubes from one box to another. And for example, before this rehabilitation, it took, I don't know, 5 minutes for the patient. And after several sessions, there was a significant decrease in the needed time. So definitely this type of rehabilitation is very helpful for them. Okay, so first conclusion. CP model as one representative of tensor decomposition is very useful model when detecting subject-specific oscillatory rhythms in the EEG signal. We need only few minutes of EEG signal from the mirror box training. Because of the character of the model, we are able to incorporate natural or interpretable constraints. For us, it's important only important to only extract the mu rhythm. But in the future, we would like to focus also on other rhythms because we have some results that, for example, some sensory motor rhythm increases after the motor imagery starts. So we maybe can combine this information during the rehabilitation. Okay, so now let's go to second part or second example, which is a mental fatigue experienced during motor imagery task in virtual reality. Here you can see a time protocol of the neurorehabilitation. One trial takes approximately 1 minute. It depends on how fast the subject is with the motor imagery. So the whole session takes approximately 30 minutes, sometimes longer, sometimes shorter. Nevertheless, these patients are usually older people. They have some additional healthy problems because of this stroke. So sometimes they are very tired, even after few trials. When they are tired, then there are many unsuccessful trials and maybe they can be frustrated and they are not motivated to continue in this rehabilitation. So we need some marker of the level of their mental fatigue so as the therapist can, for example, change the virtual environment or he can somehow modify the rehabilitation procedure or he can say that, okay, now we are going to take a short break or something like that to make the patient again motivated. So how to evaluate the level of mental fatigue? Naturally, we have some standard questionnaires which the patient can fill in. However, these are very subjective. We did this, but when analyzing the answers, we did not find it was very difficult to make a conclusion from these questionnaires. So we need something more objective. But we have information about these latent components from the CP model. So what about focusing on this information? Maybe we can find something. So a year ago, we ran mental fatigue experiment. In this case, the EEG or 7 healthy subjects took part in this neurorehabilitation in virtual reality. It were students from this faculty. And the experimental protocol consists of 3 sessions on separate days. The first one was mirror box training, because we need to know their typical oscillatory rhythms. The second one was standard motor imagery session. The students, as in the case of patients after ischemic stroke, were instructed to imagine movement of the avatar hand, and if the motor imagery was successful, they were rewarded. The third session was a control session. In this case, the students did not perform this motor imagery. They only observe movements of the avatar hand, because we wanted to separate the effect of visual, or we wanted to separate the visual and attention effect from the motor imagery. In addition, we also recorded a pre- and post-session EEG signal during resting state, each of which took approximately 2 minutes. And as I said, students also filled in some questionnaires, but the results were not meaningful, so I'm not going to present them. Okay, so now in the analysis, we used, till now, we used only this pre- and post-session EEG signal. The pre-session EEG signal was labeled as non-fatigue, and the post-session resting state EEG was labeled as fatigue, because between them there was this motor imagery session taking approximately an hour in the case of students. So we expected that after this hour they will be tired. The signal pre-processing consists of standard procedures like detection and removal of artifacts, then windowing and computation of oscillatory spectrum. Then we apply CP decomposition, and in contrast to the first example, when we focused especially on the spatial and frequency characteristics, in this case we analyzed especially temporal signatures of the extracted components. Here you can see results for the first subject. In this case, the CP model included only 3 latent components. And from the literature, we know that mental fatigue is related or most visible in the alpha rhythm. Alpha rhythm is around 9, 10 or 11 Hertz. And when you look on this first latent component, it is a representative of alpha rhythm. Also, the source of the activity is in the, we can say, occipital region. But what is more interesting are the time scores. The dashed line separates the second motor imagery session and the third control session. The red lines are average time scores during the pre-session resting state EEG, and the green one are average time scores during the post-session EEG. So the first one is non-fatigue and the second one is fatigue. This is not a something supervised, like supervised learning. It is totally unsupervised. We only wanted to see whether we can see difference between these 2 parts of data. And in the case of this first component, there is definitely a difference. And also, when you look on the profile of these time scores, we can say that somehow it represents or how the level of mental fatigue behaved in this case. Similarly, second subject, in this case, the optimal number of components was 4. Here, some differences in the pre- and post-session time scores are visible in the case of the first and the second component. The second one is okay, it is an alpha rhythm. But the first one, we can say it is a mu rhythm. So for us, it was quite strange why the mental fatigue can be visible in a mu rhythm. But this can be interpreted that between this pre and post EEG, these students performed the motor imagery. So before, the level of this latent component can be low, but in the post-session EEG, there can be some remaining effect of the motor imagery. So therefore, we can see this increase in the time scores. So this is also important that in this case, maybe someone will blindly take both of these components. But the first one in this case definitely is not related to mental fatigue, but more to motor imagery. Okay, and the last example, again, in this case, the optimal number of components was 3. And in this, the difference in the time scores between pre and post is visible in the second component, which is also alpha rhythm. Not as much visible, it is also in the first component. It is alpha rhythm. However, the spatial map is quite strange for me because the activity is not only in the occipital region, but also in frontal. So in this case, it is questionable whether we can use also this information or only this one is meaningful. So how to use this information to monitor mental fatigue level? It's the same like in the neurorehabilitation of patients after ischemic stroke. In the experiment or in the neurorehabilitation, we used the spatial and frequency characteristics of the mu rhythm as linear filters to detect level of the time scores of the mu rhythm. The same can be done also in this case. We take the characteristics of a given mental fatigue related component or alpha rhythm. We can take these spatial and frequency characteristics online, estimate these time scores, and when we see that it increases, we can say, okay, probably the patient is tired, and we can change the protocol, or we can do something to help him or her. Okay, third example, this will be something different, and it is detection of resting state EEG microstates. In a resting state, human brain rapidly switches between a finite number of stages, which we call EEG microstates or atom of thoughts. The duration of each microstate is very short. It is approximately from 60 to 120 milliseconds. In some literature, there is information that EEG microstates can take 100 milliseconds to few seconds, but it's questionable. And the transition between these microstates is rather discrete than continuous. It means that for 60 milliseconds, our brain is in one state, and then it rapidly switches to a second one. In 1970s, when this research focused on EEG microstates started, people usually take the EEG signal, look at it manually, and try to find some finite number of spatial maps representing these EEG microstates. So in the first studies, there were detected only 4 microstates, which were labeled by ABCD. The first one represents activity or positive activity in the right hemisphere in the frontal region and negative in the left hemisphere in the occipital region. B is somehow orthogonal to the first one. C represents negative activity in the occipital region, and D positive activity somewhere over sensory motor area. Later, people used computers and some advanced methods to detect these microstates. So now we know about 5 to 7 microstates, but the number is dependent on a subject, on his or her healthy status, and so on. So how this microstate or why these EEG microstates are useful? When we detect them in the EEG signal, we can compute some characteristics. For example, the time spent in a given microstate, the number of occurrences of a given microstate, or average microstate duration. And it can be found in the literature that people with some neurological problems, like, for example, Alzheimer, Parkinson's disease, or schizophrenia, have some or show some anomalies in this EEG microstate characteristics. So they are a very good marker to distinguish between healthy EEG and EEG of a man or a woman with some healthy problems. From a mathematical point of view, when we would like to detect these EEG microstates, we usually apply cluster analysis. The input is standard EEG signal, which is average referenced. It means that when we compute the average in each time point across all electrodes, then the average is 0. Then usually the signal is filtered between 0 and 30 Hertz to suppress some artifacts. And then we compute so-called global field power. The formula is here, and a graphical representation you can see here. Then we detect local maxima of this global field power. In each time point related to this global maxima, we have information about the EEG signal from all electrodes. So in each time point, we have a different spatial map. And these spatial maps, or in other words, vectors of length J, form an input into cluster analysis. The most widely used clustering method for this purpose is modified k-means. It is a standard k-means algorithm, which is a polarity invariant. Because, when we have, for example, this map, or the polarity is opposite, it is still the same microstate. In the k-means clustering, you have to set the appropriate number of clusters before applying the method. So in this case, you can use some prior information, or many researchers standardly use 4 microstates. Or you can use any method for setting appropriate number of microstates for the k-means algorithm or for other clustering method. It's up to you. Okay, so the result of the clustering can be, for example, these 5 spatial maps, and then these spatial maps are backfitted into the times where the local maxima of the global field power occurred. So now we know in each this local maxima which microstate is active in a given time point. But this is done only for this local maxima. The time points between 2 local maxima of the global field power are assigned to the same microstate of the nearest local maximum. In other words, from a mathematical point of view, when you have two local maxima, then the interval between them is divided in a half, and the first half is assigned into the microstate, I don't know, A, if it is the typical microstate for the first local maximum, and the second one, for example, to microstate to microstate B. Okay, and why I'm speaking about this, but my presentation was focused on tensor decomposition. So the question is, can we use also tensor decomposition to detect EEG microstates? Because for me, K-means, I hate how to say it, it's not a very nice method. So, and also the overall procedure, how the microstates are detected, for a mathematician, it is not very rigorous, we can say. So I would like to see whether it is possible to obtain the same or similar results also with a more advanced approach. So the answer to my question is yes, but we need a lot of math. So now will be the math. So the spatial maps of the EEG microstates, we can store them in a matrix U with in each column we have one spatial map for one microstate. So if we have K microstates, there are K columns. They are also normalized, and the second matrix will represent a cluster assignment. We can consider either hard clustering. It means that the elements of the matrix Z includes only zeros and ones. When one tells us that, for example, the time point n belongs to the microstate K. Or we can consider a soft clustering. It means that the sum over each row is equal to 1. So we can say that these elements of matrix Z are some weights or probabilities with which a given time point belongs to a given microstate. And this is a formula which is optimized during the modified k-means algorithm. It means that we would like to find this matrix Z and spatial map stored into U, so as this criterion is minimized. This product is because of this polarity invariance. Because, you know, if you have a spatial map mu k or minus mu k, we would like to have that it is the same in our case. Okay, so this is again the criterion, then lots of ugly mathematics and formulas. And the formula above can be rewritten in this form. And this is something we already have at the beginning. This is some outer product between three vectors. So it's an indicator that, okay, it maybe will have something to do with tensors and the CP model. And from the literature, we know that this one is exactly optimization criterion of a special version of the CP model, which is called implicit slice canonical decomposition, or IMSCAND. So what is IMSCAND? In the first step, we have to, in the case of the modified k-means algorithm, we had a standard EEG signal as a matrix. We have to somehow transform it to, so we are able to apply this tensor decomposition. In this case, we do not work with spectrum, but we form so-called tensor with symmetric slices. It means that in this case the tensor is of the size j times n, where j is number of electrodes and n is number of time points. And each frontal slice is is a result or outcome of the product when we take the EEG signal in the nth time point. It means that we multiply the column vector by its row version. And this is done for each time point. So the result of these multiplications are n matrices, and when we concatenated them, then we obtain this tensor. Because of the symmetry of the tensor slices, the CP model has this form. So the first and the second component matrix must be equal. And the third one, okay, it can be denoted by C or Z, but to be able to detect these relationships between a tensor decomposition and modified k-means, I use the notation Z and the same, meaning that it is a cluster assignment. So, and it is very important to mention also that this special version of CP model, this IMSCANT, was directly developed for clustering of the datasets with multiple similarity measures. And again, we can estimate the matrix Z as a sparse matrix including only zeros and ones, which represents the hard clustering, or with the elements between 0 and 1, which represent soft clustering. So, from a theoretical point of view, I skipped this derivation, but from a theoretical point of view, modified k-means and IMSCANT are equivalent methods. So we would like to demonstrate it also on simulated data where we know the exact structure. There is a MATLAB toolbox which was developed for EEG microstate simulation. So in this case, we used a prototype spatial maps, which are depicted in this figure. And the microstate sequence, it means the occurrence of these 4 microstates, was simulated by using random walk decision 3. The simulated EEG signal then consists or takes 1 minute, and it was simulated so as it is measured by 64 electrodes, which is a standard number of electrodes. And we simulated 50 trials. So in this case, we know the microstate spatial maps and also the sequence of the microstate. So we applied the modified k-means algorithm and the IMSCANT to this data, and the results from 4 randomly chosen trials are depicted in this figure. In the first row, you have prototypes, which were used for simulation. And then for each trial or for each subject, in the first row you have results from the modified k-means, and in the second row the results of IMSCANT. Yes, there are some differences in polarity, but because the polarity does not play a role in our case, we can say that both methods extracted exactly the same microstates as were generated. Naturally, these data were noiseless. I have also some results with some noise, but the results were still the same. What is the polarity measure? It is a property of the EEG microstates, because it is only a sign change, but the activity, or how to say it, when our brain is in one microstate, it doesn't matter whether there is a plus and minus or it is an opposite. It is still the same state. Okay, both methods were able to estimate or to extract the spatial maps of the two EEG microstates. And in the second step, we compared the extracted EEG microstate sequence. So in which order the microstate occur in our data. So in this case, you can see the ratio of time points which were assigned to a given microstate 1, 2, 3, or 4 by modified k-means versus the original sequence. You can see that the ratios are around 90%, so the correspondence between the true sequence and the results of modified k-means is very good. The same is true for IMSCAND, and when we computed the correspondence between microstate sequence estimated by IMSCAND and modified k-means, because we wanted to show that these two methods are really equivalent, sometimes we obtain an ideal correspondence equal to 1. Okay, this was simulated data case. Now let's go to real EEG signal. In this case, I used the same EEG data as in the mental fatigue experiment. It was the pre- and post-session resting state EEG data. The number of microstates in the case of modified k-means was, by using different methods, was set as 5. In the case of IMSCAND, it was 3. So this was the first difference in contrast to the simulated data case, because, you know, in the real data you have some noise, so different approaches can lead to different results. But to avoid some not fair conclusions based only on different number of microstates, we ran both algorithms by using 3 and 5 microstates separately. So, in this case, you can see results when we considered 3 microstates for 2 subjects. In the first row, you can see estimated spatial maps of 3 microstates from the modified k-means. In the second row, from IMSCAND. Visually, they are very similar. Naturally, it is not as ideal as in the simulated data case, but from a visual point of view, it's okay. It's okay. Moreover, both algorithms, modified k-means and also tensor decomposition, are iterative algorithms. So sometimes they can end in a local maximum instead of something better. So some numerical differences in these results are rather expected. Here you can see a result when considering 5 EEG microstates for other 2 subjects. Again, the similarity between these 2 approaches is obvious. But the problem occurred when we tried to compare the estimated microstate sequences. As in the simulated data case, we computed the ratio. In this case, we do not know the true microstate sequence because of this real data. So we computed the ratio of time points which were assigned to the same microstate by both methods, modified k-means and IMSCAND. In the case of 3 microstates, okay, maybe the ratios are quite good. The problem is, for example, in the subject number 5. But when considering 5 microstates, sometimes the correspondence is very low. And for us, it was like, why? Because the spatial maps were very similar to each other. The answer, or the hypothesis why this phenomenon occurred was that the reason are numerical very small numerical inconsistencies, which can cause that one point which was, I don't know, assigned by modified k-means to microstate 1 was assigned by IMSCAND into microstate 2. So we take the spatial maps estimated by modified k-means and use them as fixed maps in the IMSCAND algorithm. So in this case, in IMSCAND, only the cluster assignment was estimated. And then we compared the estimated microstate sequences between the original k-means results and these new IMSCAND results. And now you see that the correspondence is very, very good. So the reason where these numerical differences. Again, when we change the order of the methods, when we took these spatial maps from ImScand and used them in the modified k-means, so only this cluster assignment is estimated by backfitting. Sometimes in some subjects and some microstates, we achieved the correspondence equal to 1. So, modified k-means and special version of CP decomposition called ImScand are equivalent methods. We proved it both theoretically and practically on simulated and real data. And why this is useful? As I said, modified k-means is a very simple method. Sometimes it is not very stable, and it can converge to a local optimum instead of global. In the case of tensor decomposition are more advanced methods, they allow us to incorporate many constraints or to use some more advanced algorithms to stabilize the solution. And also, when considering ImScand, we can use, or we have many more possibilities to choose many more methods, for example, for setting appropriate number of microstates and or to perform some post hoc analysis from this tensor decomposition era. And as I said at the beginning, the EEG microstates are believed to be discrete. So our brain is in one state and then rapidly switches to another. However, there are some studies, some current studies, which are not very satisfied with this result and try to prove an opposite. However, there used many simplifications, dimensionality reduction methods, and so on. So it is very difficult to decide whether these EEG microstates are discrete or continuous. But maybe application of these tensor decomposition methods can in the future bring answer to this question. So I think I'm not having time for the last part. It's up to. Okay. Okay, so the last part, how to use tensor decomposition to remove eye blinks from EEG signal. When EEG signal is recorded during eyes open condition, as it is in our neurorehabilitation of patients after ischemic stroke, because they need to observe this virtual scene, so it is impossible to have closed eyes. The EEG signal is contaminated by eye blinks, especially the frontal electrodes. If we do not remove these eye blinks, then the analysis or the results which we obtain from such a signal are not meaningful. Standard methods how to detect and remove eye blinks are, for example, the Grattan-Coles and Donchin algorithm. It is a regression-based algorithm, and its disadvantage is that we need information from electrooculogram. So in addition to EEG, we need also another signal, which is usually not available. Sometimes we use, instead of it, signal from one of the frontal electrodes, but you know, this replacement, the results are not, or by using this method, we are not able always to detect and remove all eye blinks. More widely used is independent component analysis for the eye blink detection and removal. However, I will show also one example. This method, okay, it removes eye blinks, but on other hand, it can contaminate the data by artificial oscillations. So we want to clean the data, but somehow we contaminate it with something different. So a new method for these specific cases is really needed. So we developed so-called spectre algorithm, which is a signal spectrum tensor decomposition and eye blink removal. In the first step, we standardly form or compute the tensor. So we divide the EEG signal into overlapping windows, compute the spectrum, and the values are concatenated into a tensor. Then we apply the CP decomposition and try to find latent components which are related to eye blinks. The properties of eye blinks are that they follow, for them, there is no specific frequency, but they oscillate over a wider frequency range. So therefore, there is no narrow peak in the frequency signatures. Then the activity is in the frontal region, logically. So we would like to have, so for example, this one definitely does not represent eye blinks. And we can either visually compare, for example, the time scores with the signal from the frontal electrodes where the eye blinks are visible, or we can use some automatic methods based on some properties, because these eye blinks, they are very short bursts of hour amplitude. So there are many methods based on amplitude thresholding, or I don't know which other properties which are able to automatically decide whether this latent component is eye blink related or not. Okay, so when these eye blink related components are chosen, we have to remove them from the data. Again, there are many possibilities how to remove these components from the tensor. However, we observed that the best results are obtained by a simple subtraction. No big science, simple subtraction. But there is a problem. When we subtract these components from the tensor, the result can be negative. However, our idea was that after removing these artifactual components, we obtain a tensor representing spectrum of the clear signal. And spectrum of the clear signal should be non-negative. So these negative values are problems, because we would like to transform back this tensor into signal, and methods developed for such a transformation are not able to work with negative values. My first idea was to replace these negative values by zeros, but the results were very bad. So we had to do something different. And it is, we have to add 2 intermediate steps into the algorithm. After the spectrum computation and tensor construction, we apply logarithmic transformation. So now our tensor is no non-negative anymore because of this transformation. Then the next 3 steps are the same. It means CP decomposition, eye blink related component selection, and component removal by subtraction. Now, because the tensor is not non-negative, when the subtraction results in something negative, it's not a problem. And then we apply inverse transformation. So now the new tensor representing spectrum of the clean signal is non-negative, thanks to this transformation. And we can apply spectrum to signal transformation. Again, in the literature, there are many approaches, but the best results we obtained by this one Griffin limb-like phase recovery via alternating direction method of multipliers. Here you can see a comparison of the original eye blink corrupted EEG signal, which is depicted in gray, and it's a clean version from the spectral algorithm, which is in black. So all visible eye blinks are successfully removed. Now let's go to compare spectre with traditional approaches. Here you can see the results of the Gratton-Coles algorithm. Both algorithms were able to remove eye blinks, but if you look on the results of Gratton-Coles, some part of the eye blinks is still present there. But what is a problem here? The spectrum of the original EEG signal is depicted in gray, and the spectrum of the cleaned signal is depicted in black. When we remove something, it means that the clean spectrum should be equal or should lie below the original signal spectrum. But this is not the case here. You can see here from 15 to 30 Hertz, the black curve lies above the gray one. So Grattan-Coles removed something, but also add some oscillations. So in this case, the signal is definitely not clear. In the case of Spectre, this problem is not present. Now let's focus on a short time interval with no visible eye blinks. So in this case, the reconstructed or cleaned signal should be approximately the same as the original one. So the original one from this short interval is depicted in gray. Here are the results from Grattan-Coles and from Spectre. You can see that Grattan-Coles definitely there is some oscillation added, because it is either there is an increase in the amplitude, and it is also more dense. And again, also we can see the increase in the spectrum. Okay, what about independent component analysis? Independent component analysis is a very powerful method for eye blink detection and removal, but I chose one example where it produced inferior results. Here you can see that the method was not able to remove eye blink at the very beginning of the EEG recording. And again, the contamination by artificial oscillations is present. When we focus on a shorter time interval without visible eye blinks, definitely you can see that ICA contaminated the signal in comparison to the original one. But when we compare the original data with the results from Spectre, visibly they are very similar, and when we compute the correlation, then it will be quite high. And also, when you compare the spectra, here the results are very bad, because you see that the whole spectrum of the clean signal lied above the original spectrum, and this is really what we this is something which we wouldn't like to see. So, final conclusion. Tensor decomposition can be also used for detection and removal of eye blinks. Spectre algorithm, as it was developed, its idea was not to compete with ICA or Grattan-Coles and Donchin. It was developed for specific situations in which the traditional approaches fail to remove eye blinks. And as I demonstrated in this case, Spectre can help us. In addition to eye blinks, we can also remove other artifacts of oscillatory nature. For example, when you have some, 50 Hertz oscillation from the electricity, you can successfully remove it by Spectre. But on the other hand, Spectre is not able to detect and remove artifacts which are very sporadic or which have some non-oscillatory properties, we can say. It is not developed for these cases, so these artifacts have to be detected and removed by some other methods. So that's all. Thank you for your time and your attention, and if you have any questions, I will try to answer them.